Welcome to this tutorial on waveform diagrams. Because it is difficult to visualize a sound wave, we use a diagram to represent its pattern of changing air pressure over time. These diagrams are called waveform diagrams, and they have become the standard way to represent sound pictorially in print and software. When a source expands and contracts absolutely consistently, it is said to be moving in simple harmonic motion. The wave it creates is called a sine wave. The waveform diagrams in this video use sine waves. We could have used any type of wave, but a sine wave is nice and simple and helps us to show how the diagrams work. A single isolated sine wave can only be created by an electronic sound source, a so-called oscillator, which can create an electrical pressure sound wave according to the strict mathematical principles of electronic design. However, a complex wave can be considered to be made of hundreds or thousands of individual sine wave vibrations. Waveform diagrams contain the following elements: a bipolar amplitude axis showing normal air pressure and silence, increasing pressure and increasing amplitude, and decreasing pressure and increasing amplitude. A time axis which can expand and contract to show any duration from a few milliseconds to several hours. A curving line which plots the changing pattern of air pressure energy from compression to rarefaction. One or more cycles. Wavelength. And finally, frequency, or the number of cycles per second. The amount of compression and rarefaction of the air is expressed as the amplitude of the sound wave. It is the volume or loudness which the ear perceives. As long as the air pressure is changing, rising and falling that is, sound will be heard. The greater the rise and fall, the louder the amplitude and volume. It is critical to note that waveform diagrams show amplitude on a bipolar axis, and that silence is shown as a flat horizontal line, the horizontal axis. When a source has expanded and contracted once, it is said to have cycled. This is a single vibration. Almost all sounds cycle multiple times. The physical distance between two adjacent points on two cycles of a sound wave is called the wavelength and is denoted by the Greek letter lambda. Because a sound can vibrate at many different speeds or frequencies, this wavelength is variable. The wavelength of sound at 20 cycles per second, deep bass, is approximately 17 meters. The wavelength of sound at 20,000 cycles per second, high treble, is 1.7 centimeters. Wavelength is critical to understanding how a sound behaves when it encounters a physical obstruction. The speed with which the source vibrates is known as the frequency and is expressed in hertz or cycles per second. 1,000 cycles per second is equivalent to 1,000 hertz or 1 kilohertz. Humans can hear frequencies between 20 Hz and 20 kHz. This is known as the audio spectrum and is covered in a separate video tutorial. Waveform diagrams are the standard way to not only show waves pictorially in print, but also in audio software. So whenever we are recording, editing, processing, or synthesizing sound, we can see a visualization of the sound wave. The script for this tutorial with accompanying images can be found at our website projectstudiohandbook.com. And finally, don't forget to join our mailing list to receive notification of new videos, blog posts and subscriber-only extras, and also subscribe at our YouTube channel and social media pages. Thanks very much for watching.